Hello, everyone. Welcome to the Kamenev seminar. And today we are very glad to have Professor Alex Kamenev from University of Minnesota. And Alex has a very broad interest in many things, including field theory of non-Euclidean physics, strongly correlated electronic systems, and also quantum information. And today, Alex will tell us about quantum optimization and many-body localization.
Thank you. Hey, thanks for introduction. First of all, it's so nice to be back here. So many people. So I want to tell you about our attempts to play with quantum optimization. How quantum it is, it's sort of debatable, but nevertheless, I hope you'll agree with me that it's a nice game to play. Great. So I'm doing it with three of my current or former students, Hao Zhang, Han Teng Wang, and Shu Chong Ye. And D-Wave machine is sort of playing a big role in these games, funded by NSF. Which now they have now sort of a scheme to allow you to play with quantum computer you want. Right. So the motivation is sort of an attempt to do something useful, semi-useful, with all these wonderful machines, which are around and to some extent working. And as I said, thanks to NSF, you can access any of them and do experimental physics in a sense with these devices. And we are mostly playing with this one, which is probably least quantum of all of them. Okay, so the problem which we decided to think about, and D-Wave machine is solely built to solve this one single problem, is optimization. Now, what is optimization? Classical, there is nothing quantum about this problem. So you want to find, computer scientists will call it bit string. We call it state of Ising spins, plus minus ones. And this state of Ising spins should minimize certain cost function, which is a Hamiltonian in our language. So as an example, you can take right. So the simplest one you can imagine is just pairwise interaction of Ising spins with some metrics, connectivity metrics Jij. For example, if it's a random matrix, then it's a famous Sherrington-Kirkpatrick model. If it's not a random matrix, but something else, it can encode certain class of optimization problems which you may want to think about. Right? So again, the problem is purely classical, but there are 2 to the power n, nevertheless, possible answers, just plus configurations of plus minus ones, which are, you can call them many-body eigenfunction of functions of your Hamiltonian. So these classical eigenfunctions are perfectly localized in a many-body sense. They're perfectly localized in the basis of bit strings, of plus minus ones. No superpositions, no nothing. Nevertheless, the problem is sort of NP-complete in a sense that if you want to brute force find the best possible configuration, you need to spend exponentially long time doing it. Now, of course, that's not the way people try to solve these problems. So one of popular ways doing annealing, and the way it works is that you start from some more or less random bit string spin configuration, then you flip one spin, you check if new energy is better than the old one. If it is, then you accept, or if it's not, then you reject and do it again. or you can do it with certain probability, or you can flip two spins. So there are variation of this procedure, but all of them lead to some lowering energy, and it would be all good and nice, but the reality is that it's a spin glass problem. So this procedure is necessarily bringing you to some local minimum, and you're getting stuck there. Yeah.
Can you remind me if these coefficients Gij are local or not?
Not necessarily.
Not necessarily.
Yeah, I'll tell you about specific machine which we are playing with later, how it works.
Does it work faster if it is local?
Again, not necessarily. As long as you deal with spin glass and nobody quite knows what is exact criterion of a spin glass, but as long as it's glass, locality doesn't buy you. At least I don't know how to use it to simplify it. Very good. Right. So the problem with this game is that you necessarily deal with local minima, and if you want to find a better minima, you need to flip many spins, generically of order n spins. So you measure distance between this local minima in number of spins which you have to flip, which is called Hamming distance. And typically all these minima are order n Hamming distance away from each other. And simple quantum annealing, like classical annealing, I'm sorry, like this is not going to tell you how to go from here to there.
Is name of a person?
Hmm?
Is Hamming the name of a person?
Yes.
Yes. So it should be with capital, sorry. Yes. Should be. All right. So now quantum mechanics came into the game with beautiful idea that now we have tunneling between different minima. So maybe one can explore quantum mechanical tunneling as opposed to thermal activation, which is what classical annealing try to explore. Now, how to involve quantum mechanics? You add something which is non-commutative with your optimization, Sherrington, Kirkpatrick, whatever optimization problem. So the simplest one is to add sigma x's.
Are you talking about the chain
Uh,
or plane or what's
So for now, it doesn't matter, but in a specific application, which I will show you, it's a three-dimensional array of qubits.
So before adding this term, you talk about three-dimensional Ising model.
Yeah.
Classical.
Yes. Not Ising, because if all Jij's are positive, that's not interesting.
Ising is this way. Plus
Ising with random.
which is already sufficiently complicated
Yeah.
before adding this.
Yeah, no, this term is supposed to be a tool to solve it. Okay, it's not. I'm not trying to complicate the model. I'm trying to solve a simple model with this. All right. So why is it going to help, or is it going to help? So idea is the following. So you do simple quantum annealing. The idea is this. So let's apply very large transverse magnetic field. Very large. Okay. Then we almost know the ground state. It's a state of all spins oriented in x direction, which is a democratic superposition of all possible bit strings in your disposal. So this state is completely delocalized in this basis. Okay. So not only we know this ground state, we also know that this ground state is gapped from the rest of the spectrum, because the simplest excitation is a flip of one spin, and if px is large, then flipping spin is cost you a lot. Okay, so you know the ground state, you know it is gapped, so you initiate your machine into this known ground state, and then you slowly decrease your magnetic field, and then according to adiabatic theorem, you will follow the ground state, And eventually, when Bx reaches 0, you arrive to the ground state of the problem which you try to solve. Okay, so that's a wonderful idea, which seemingly give you a possibility to find true ground state. Okay, now the devil, of course, is in the details. Namely, along the way, you need avoiding crossing situation. And these avoiding crossings are exponentially narrow. So if you really want to explore a diabatic theorem, you need to do it exponentially slow. Okay. And then the time scale to go from here to there is again exponentially large. And if so, then you didn't gain anything else, any advantage. Okay, so the question is, can we do a little bit better than that? Is there still a possibility? Okay, so that's a nice question. So what's the answer? So the first statement is that there is no free lunches. So if the problem is still exponentially hard, and if you want to find true ground state, there is no choice but paying exponential time. So I think that's accepted by now. So mathematicians are sort of struggling with exact coefficient in the exponent. As some time ago, the best estimate was this 0.2, which is a big deal. It's much less than 2 to the power n, but it's still exponential. Okay.
This is exponentially better than.
It is exponentially better, but still exponentially costly. So it's glass half full, half empty.
Alex,
Yeah.
we're not averaging we don't take randomness of J's. We just fixed the configuration.
Right. So every configuration of J is a specific optimization problem which you try to solve. Okay.
Not what we usually call spinous.
Yeah. So, for example, I was telling this story over the lunch. Apparently, MasterCard decide every transaction is if transaction is fraudulent or real by running this D-wave machine. So every JIJ configuration, so for every specific transaction, MasterCard generate matrix JIJ, and then somehow finding the minimum of this thing tells them if it's a fraudulent transaction or not. Yeah, and that's the fastest way for them to arrive to a decision, but no averaging, given transaction. All right, now one can change slightly to be slightly more modest, namely saying that I don't want to find true minima. After all, who cares? I mean, there are very many states close to the ground state. Let's find a state sufficiently close to the ground state and call it a victory, right? So then what you're looking for is for approximate optimization scheme, which will approximate true ground state with certain precision delta epsilon, with certain energy.
Are you requiring, is there any requirement on the distance in the configuration space?
No,
So they could be completely different.
it may be very, very different from the ground state, but the energy will be
Yeah,
sort of
sure.
exponentially close to the ground state. You say it's good enough. Okay. But I'll tell about distances much more later. Yes, Luca.
So here, the locality probably plays an important role in the density of the spectrum close to the ground state, right?
No, at least not what I know. Spectrum is exponentially dense in any case,
No, but if you have a local Hamiltonian,
still exponentially dense.
the gap will be order 1 over L or 1 over size, not exponentially small.
Well, you want completely ordered Hamiltonian.
Yeah, okay, maybe let's first say complete. Okay, so you're saying, okay, the disordered
Yes.
local will have an exponentially close.
Yeah. Like a slide K.
Right, no, but there's an order of limits, right? You have, I'm talking about a model with that's local, but the so an actual spin chain, let's say qubits, on a string. So there, the spectrum is exponentially dense in the middle of the spectrum. But close to the ground state, you only need the splitting, right? You only need the gap to be adiabatic compared to the gap just above the ground state.
Yes, that's a good point. If you can keep all the way very close to the ground state or at the ground state, then you only worry about gaps near that. But in disordered system, they happen to be exponentially small.
Do you want a constant approximation fraction or absolute performance guarantees? Because I would imagine this is much harder than like this whole thing divided by 8GS, right?
Say it again.
Do you want the difference of the cost functions to be below a certain number, or do you want the ratio of the differences to be below a certain?
Well, that's a good question, but not to complicate things, let's just think about absolute value of energy difference. With the precision I'm going to talk about these things, that doesn't make a difference. Okay, so if you're slightly more modest, then what you can show that your running time to sort of approximately solve this problem scales algebraically with both system size and precision you require. Okay. Now that statement is actually true for both classical computation and quantum computation. In both cases, that's the case. So now the question is whether quantum exponents can be more sort of favorable, beneficial to us than classical exponents. Okay, and it's not clear whether it is the case, but some people, including myself, want to claim that yes, it is the case. That quantum exponents are better than what you can achieve classically. Right, and moreover, I want to claim that in some sense, these exponents are related to critical indices of many-body localization transition. Again, I'm not claiming that I have a proof, but that's sort of a conjecture. So D-Wave people run experiments and they claim that the slope which they see in their optimization is better than both simulated annealing and simulated quantum annealing. So true quantum computation, according to them, has a better slope, and they take it as a proof that quantum algorithms, indeed, quantum approximate optimization algorithms are indeed better than classical. But again, it's just for some specific algorithm. Nobody knows if it's generic statement. Okay, so now here is an idea how to make this machine working better. And I'll tell you first this rough idea, and then I'll show you experiments which sort of show that it indeed not a bad idea, probably. So first of all, you can modify your classical problem, namely, imagine you find a good enough local minimum somehow by classical annealing or by whatever mean. So then you bias your system by applying magnetic field in Z direction, which is collinear with all the spins in your chosen local state, local minimum. Okay. So then as a function of this Z magnetic field, the state which you have picked up to take field collinear with all the spins goes down in energy with a slope which is capital N, because all the spins are collinear with the field. Okay. All other states also depend, their energies depend linearly on my applied field. It's still a classical problem, but the slopes are of order of square root of n, because that's a completely different local minima. They have spins which are sometimes collinear, sometimes anti-collinear with applied field. Okay, clear? So therefore, by applying this longitudinal field Pz, I can pretty soon make any state I wish. I can make it a ground state of that artificial problem. And not over it will be a ground state, it will be a gapped ground state. Everybody else will be far away from this state. Moreover, this transition point between my state being in the middle of the spectrum and being a ground state is essentially first order transition where levels are just cross. What else? Yes, what else is important that along this way, I have plenty of crossing, not avoiding crossings, but crossings, but all these crossings are with the states which are below in energy, in a region of energy. I cross only those states which are below my state. Okay, so therefore you can take advantage of this. So I will skip that. So let me go about it. Right. So before I tell you how I want to go about it, let me speculate about phase diagram of this thing. So now I will think about extended. So this is my problem which I try to solve, optimization. Now this is biasing towards given specific state which I have chosen, and that's my quantum field, which is a transfer state. Okay, so now I'm sort of speculating the shape of the phase diagram. So if I increase my longitudinal field, as I just explained on a previous slide, at some point I pass first order transition where ground state become gapped, and moreover I know what is this ground state. It's just written here. So that's this point. Now, in another hand, if I increase magnetic transversal magnetic field in Bx direction, then at some point I go from spin glass phase to a paramagnet to the state again gapped because now ground state is all spins in X direction, and here I encounter localization, delocalization transition in my many body state of this big strings. Okay. So now you can sort of speculate that these two phase transition lines meet at some three critical point. So here I have a gapless spin glass. Here I have gapped but localized states, and here I have gapped but delocalized states. And one can hope, and for simple models you can show it, that this transition is a second order transition, and this one, as I argued, is a first order transition. Okay. So then the speculation is that you can arrange kind of refrigeration cycle, pretty much like what we do in our kitchen. You run this working substance through evaporation and condensation transitions, right? So here your working substance is your spin system, and you melt and refreeze it through certain sequence of the phase transition. So in particular, the cooling cycle looks like this. So you first increase the longitudinal Bz. So your state goes down, become gapped state. You sit in this state because all these transitions were harmless. There is no avoiding crossing, it's just crossing. So then you increase X magnetic field. So you go up here, being always in a gapped phase. So you can do it relatively fast. your ground state is gapped from everybody else, and no transitions expected. Along the way, now your problem is quantum, and crossings are removed. You have avoiding crossings. Okay, and now you go back through the second order transition. So you go back, and now you start experience all the Landau-Zener transitions. But mostly, and there is certain statistics which I will show, your transition are with states which are with the states which has smaller energy than states you started from. So you have an increased probability to end up in one of those states, or maybe come back to your initial states, and much smaller probability to end up somewhere here. Okay. So then the idea which we actually run is to start with some local minima, run this cycle, do measurement, find new state. If energy of this new state is lower than what we started from, we take it as a new reference state, run it again. If it's higher, then we just repeat previous attempt. So this way it sort of resembles what we all like in our teaching. Okay, that's simulations of all this energy levels. I'll probably skip. So this is a small statistics. What is the probability to end up in higher energy versus lower energy as function of the slope of this triangle, which I find. So if the slope is too small and you refreeze it for the first order transition, then basically nothing happens. Once you start refreezing it for the second order transition, there is an increased probability that you end up in a higher energy state. But if you keep yourself very close to this critical point, then you sort of can go between the springs.
Alex, excuse me. So let me understand. So you pick up some state which you think is good and improve it. Right?
Yeah.
But if the real state, you think that you may reach some metastable state.
Yeah, all of them.
But maybe the much better state corresponds to entirely different
Yes. Not made.
configuration of the signal. Then by this method you will never reach it. You will
never
improve what you already poised
Yes.
to choose.
Yes.
But if you choose wrongly and it's much lower,
Yes.
what's you going to do?
Yes.
You improve something which may not be necessary
Yes.
to improve.
Yes. You're completely right. So I'll show you confirmation of precisely that. There are ways around it, but again, it's never will give you the best. It's only give you better than anybody else.
But the glass slide between minima, trying to find the best things by doing this in 1,000 years. And you?
But we do it in milliseconds. I'm not patient enough.
I have a question sort of related to these locality issues that were brought up earlier. Does the locality enter in determining the exponents of the MBL transition?
I don't know. It should,
Yeah.
but I don't know how. Yes.
If I did like just simulated annealing with your protocol, how does that compare to the quantum case?
Well, we definitely do find much deeper minima than simulating annealing. So what we do in milliseconds, D-wave machine, not we, but D-wave machine does in milliseconds takes hours and hours of classical annealing to find states that deep.
But that's also with your refrigeration cycle protocol.
So our refrigeration cycle works better than what D-wave people use for MasterCard applications.
No, I guess I'm not conveying my idea correctly. What I was trying to say was I have standard simulated annealing and I have like the quantum version, and now you have a different quantum version.
Yes.
If I just do the classical analog of that, Because I just have Hamiltonians as a function of time, and I will like do simulated annealing along these triangular trajectories.
We didn't try to do it. So,
But that's a more fair comparison than it is, because you are being more clever than the D-wave people, right?
yes, I agree. I mean, my feeling is that that would be much slower. Just with experience with the standard quantum annealing versus standard classical annealing, it's just hours and hours of difference. Okay, so let me tell you a few words about what D-wave people sell us. So they have a processor with that number of qubits. So in principle, this Jij matrix should be 5,000 times 5,000. So this is what 25 millions elements in a matrix. In reality, they can operate only with 40,000 elements out of 25 millions. So that means that each qubit is connected with about 18 neighbors. And so the geometry is that we have 12 layers. Each layer is more or less 20 by 20. So that's 400 qubits spins, let's say, in a layer, and then 12 layers, that's more or less 5,000. Okay, so it's a kind of a three-dimensional toy with that many spins. Now, spins are probably classical in the sense that their decoherence times are bad. So in reality, this machine probably, as far as I understand, solving Landau-Lifshitz-Gilbert equations for precessing spins. Okay. But what they do, they can apply transverse fields, so they force the spin to precess around transverse field, and then it dissipatively converges either to state up or to state down. And by doing it, it knows to find very good minima. Okay. But quantum language is probably more familiar to us to discuss this kind of physics. So let's stay with quantum language. So if you do simulated annealing, so you start from spins all x, and you decrease magnetic field, you find the histogram of states, pretty much Gaussian, and then you run it. I think in this experiment we did it 2,000 times, and then you pick up the lowest energy state, okay? and you call it your solution. Okay. So in this diagram is this best state which we have one can choose with conventional quantum annealing is plotted here. Now we run our cycle thing, so we started somewhere there, and then we come here, and pretty soon we do better than what D-wave people know to do. So in the end of the day, it converges to some state, and you call it your approximate solution. Okay? So we can then, with an equal number of computing time, we can move solution down energy in about 1 sigma, which is not too good, but also not too small. If you try to do it to gain another sigma in a conventional way, you will have to run 10,000 more iterations for this statistic to generate something here. Okay, we can do it in much less number of generations. So now that's a sort of advertisement also graph. We have 50 problems, which 50 matrices Jij, which we call standard whatever test algorithm problems, and this is energy difference between what we think is the best solution for these 50 specific problems and what we could find using our algorithm. So in 42 out of 50, we found energies which are less than what we think is the best energy. Okay. Nobody knows what's actually best energy for this problem, because for 5,000 spins, you really don't know what's the ground state. Nobody knows. Okay, so now to Paul's question, whether you go far away or you explore a local vicinity. So you're right, you mostly explore the local vicinity. So what is plotted here is Hamming distance with capital H along the horizontal axis, and energy gain or loss. So initial state always the same, and it's denoted by the dashed red line. So we start always from this and run a cycle, and then we find states sometimes with better energy, sometimes with worse energy, and then we measure Hamming distance between my initial state and the state which we find. Okay. So what we see is that if you want to lower the energy, we can only do it if Hamming distance is sufficiently small. Sufficiently small is about 200. In all these cases, it's about 200. So some mysterious number. We don't know where it comes from, but as long as we explore that vicinity of local minima, we can find better states. Now we can find local minimas which are far away, but those are typically have larger energies. Now, here we can easily find local minimas which are 3,000 away, but none of them has energy better than what we started from. Okay, we don't know why it is the case, but yeah.
So should I think of just the Bx's and the Bz's as like hyperparameters that I should think of when I pick a like, do we know how Bx and Bz scale with n?
No, we don't, but you sort of do optimization of parameters of your cycle on the fly. So you run a cycle. If you don't find better minima, you change your Bx, Bz.
Is there like a schedule for Bx and Bz as a function of number of cycles?
Again, yes, we run certain protocols. I'm not saying they're totally optimized, but you can imagine that you can. So depending on what are Bz, which is different panels here, and Bx's are different colors, you see that I'm either relatively localized or almost completely delocalized. But in any case, the better minimas which I found are, as Paul mentioned, they are not too far away from my initial minima. And we don't know where this number 200 is coming from. Now, next what we do, we start from some local minima, we find another one. Sometimes it's better, sometimes it's worse. And then we analyze what's the difference between these two local minima. Namely, we look for spins which were flipped between the two. So number of spins which are flipped is precisely by definition my Hamming distance. Okay, so now I take all the spins which were flipped, and I see if they are isolated spins or they form sort of connected clusters, connected in the sense of Jij, matrix Jij. Okay, and what we find is that in all minimas, there is basically one or sometimes two big clusters which take majority of all the flipped spins. They are all lumped into certain clusters. Okay, so let me see what I want. Yes, so now for every pair of local minima, we can analyze this structure of clusters. Okay, and then we plot probability distribution of these clusters. So this is a cluster size normalized to the total Hamming distance, namely if it is 1, that means that all flipped spins belong to one and the same cluster. If it's, I don't know, 1/2, then means that this cluster take half of all flipped spins. Okay, and we have pretty big statistics and plot all those, and it's not sort of follow the power law distribution, namely it's almost -2 power. So like Lorentzian distribution, that's a probability to find a cluster of a given normalized size. Now, since it's a pretty modest power, that means that whatever you do is dominated by rare. There is no meaningful variance you can calculate in this distribution. So it's all dominated by the tails. So what else I can show you? Yes, so that is another attempt to understand the geometry of these clusters. So here we take local minimas in blue and calculate how many clusters. So you have 2 local minimas. They are at the given Hamming distance between small from each other, and we calculate how many clusters are inside. And here is an experimental result, which we generate many local minimas, and we analyze cluster structure, and that's an experimental result. Now, if we take not a local minimas, but arbitrary states of your spin systems, again, with a fixed Hamming distance, pick any 2 states with a given Hamming distance, and analyze how many clusters you find, you will see the orange line. Okay. Now, what's the orange line about? So if you take, if you flip, I don't know, 500 spins, then most probably they are completely uncoupled. So you will have 500 clusters. Okay. On the other hand, if you flip all 5,000 spins, then there is no choice but for all of them to be coupled in one huge cluster. Okay. So if you do it randomly, that's what you measure. If you take only local minimas, then what you measure is something completely different. So that's supposed to tell us something, which I'm not sure what, on how local minimas are built as opposed to random states. And ideally, that should tell us something how to find these local minimas. So that's
What
pretty
determines where the center of that peak is?
First of all, total size of your machine, and second, connectivity, depending. So that's all this data for specific connectivity which D-Wave produce. So that's the same pretty much data plotting size of the biggest cluster as function of the Hamming distance. So here you see again the big difference here. So if you look for only local minima, then the biggest cluster is pretty much equal to total Hamming distance. You see that they are connected by one big cluster. If you take random states, then you don't see big clusters at all. So again, that means that local minima, they are in a sense very non-random, which is not a surprise, but still nice that you can measure it. Okay, so then we can start, doing tomography of all local minimas and comparing it if it's what's the word? Have thousands and thousands of them. what escaped me. For Sherrington-Kirkpatrick model. No. Okay, never mind. Ultrametricity. If it's an ultrametric picture or not. For Sherrington-Kilpatrick, it should be, since we have a finite distance spin glass, it doesn't have to be, but it's actually very close to being ultrametric. We don't quite know why. No, right. So then there are other games which I will probably not go into much into details. You can sort of engineer spin glasses with a given predetermined set of local minimums. So you can engineer metrics Jij such that it will have p minimas which you know in advance, and now you can try and see if the machine can find this predetermined minima, which you know but machine doesn't, and that's what we are currently. There are certain, subtleties in how to do it, but that's what we're currently busy. So probably try to finish here. So what I'm trying to tell you, so that you can play this game of thinking how to cool spin glass in a quantum way, not in a classical way, but in a quantum, but by melting and refreezing glass through certain phase transition points. And you can think how to make this cycle most advantageous to your cooling procedure. And it, in principle, allows you to find approximate minima in the time which is algebraically, scales algebraically with precision and system size. And supposedly good idea to do. And what we actually need to understand is better way to connect to specific big clusters which we sort of identified through this procedure, and teach the machine how to flip big clusters in the most efficient way. But it's a nice toy. You can at least do experimental studies of classical spin glasses. Probably much more efficient than in traditional condensed matter setup. Yeah, that's it.
Question for Alex?
Like in classical Monte Carlo, people think about like Wolf cluster updates and so on to get over the fact that you have critical slowing down near the phase transition. Do you suspect something like that will also help here, or finding the cluster itself would be very difficult?
Find the cluster is certainly very difficult, but once you know that there is just one or two such clusters, maybe can guide your search.
Yeah, you had a picture of the D-wave. It looked a bit like a lattice. Was that the?
It's a three-dimensional lattice, more or less.
So it's kind of mostly local and nearest neighbor interactions.
Yeah, it's definitely physical local connections.
Yeah.
Some of them are horizontal, some of them are vertical.
Yeah. But you said there is still kind of 19 or 18 connections per set on average.
Right. So a given qubit, if it is not close to the boundary, is connected to 18 neighbors in some way, which will tell you how exactly it is connected.
Yeah.
If I study, unlike Erdős-Rényi graph, like if I have some connectivity graph like given by the D-wave machine, do the spectral statistics of clusters and so on follow some statistical model of like cluster growth on the graph?
So the answer is I don't know. We can compare it with what people calculated with Sherrington-Kirkpatrick thing, and it's sort of surprisingly close.
Wouldn't you expect the statistics to be different because in Sherrington-Kirkpatrick you have very long range connectivity,
Yeah,
which you don't have here, right?
Yes.
But still the exponents you say are very close.
Well, again, it very much, the answer very much depends what specific quantity you look for, because if you naively, in Sherrington-Kirkpatrick, it's always just one cluster if you just naively. But if you sort of have some threshold, what is connected, what is not connected, then it's actually pretty close to Sherrington. Don't point.
Does this algorithm of driving around the phase transition, would that also work classically?
Well, those are quantum phase transitions. So
Right, but I assume you could replace the field that's driving superpositions with temperature or something and then drive around a tri-critical point like that. Has anyone done that?
not what I know. So the thing here is that we sort of think it is important that one of these transition is first order and another is a second order. And I honestly don't know if you can arrange it purely classical. Maybe.
Still have time if there are more questions. Note that things early, please.
What is many-body localization? What is it, many-body localization you mentioned? In the title, but not in the talk.
Well, so that's.
Or maybe I missed it. I probably missed it.
So that's the way I find convenient to think about many body states of your quantum model. So once you add transverse field, your eigenstates become superposition of many simple qubits. Okay. Now this superposition may be either sort of more or less democratical average of all available 2 to the power n states, or they may include mostly just few states and everything else is just exponential small tails. Okay. Pretty much like Anderson localization that tells you in a side basis whether eigenstate is superposition of many sites or just few. Okay. So same here, but in a basis of bit states.
Yeah, I think I've missed like what the final result was, like compared to the Montanari result, like what were the exponents for the delta and n scaling?
Yeah, very good. Again, we don't know, we can change n. So in Montanari, n is to the power 2. Okay, so we don't know. I mean, we have 5,000, so we cannot can't n.
No, but
I mean, we can do
turn it off?
Hmm?
Like, can you just turn couplings off and do it for like 1,000, 2,000, 3,000?
In principle, yes, we didn't do it, but I suspect that it will be too smaller sizes to have anything sort of decisive. Now, for delta, for precision, Montanari doesn't give you anything. And I didn't find any mathematical statements about this second exponent. So as a result is that I don't know if they are doing better or worse than best classical algorithms.
No more question, let's thank speaker then.